Hello, everyone, and welcome to our second lecture on the use of models in climatology. We're going to get a little bit into the applications, although that's mostly what we're going to be covering next week. But I do kind of want to talk about sort of the data behind it, or how do we validate these models, and use that as a launching point for talking about future models. All right, so first quick fun fact of the day. This was done a couple of years ago, actually, by my colleague up there in Alaska. Super fun, right? Because basically he said, "Hey, how do you keep a constant 70 degrees is sort of like the happy temperature for most of us? Can we design a road trip based on climatological averages, so that you're always at about a 70-degree normal high temperature?" And this is what he came up with, and it's pretty darn awesome, right? You kind of see where there's only a few places, so you're starting off pretty slow down here, and in the winter months would be only about here, right? Still South Texas. But then as you move up into the year, you can kind of get all the way up into North Texas and almost Oklahoma, and then you got to scoot all the way over here to the East Coast and the foothills of the Appalachian Mountains by May, and then you got to scoot up to the northern, the Great Lakes region by June, and then you got to make it all the way down to sort of Rocky Mountain National Park by July, and stay in the Rockies August and September to keep at the 70-degree normal. And then you got to go all the way back out to Nebraska, where they have milder falls by October. You swing back through the panhandle of Texas by November, and then you can kind of head for Vegas in December and end up in Southern California. Certainly there are multiple options here, but I love this map. It's so cool, and someday when I retire, if I make it to that point, I can't wait to try to do this because it seems so fun. All right, there's your fun map or fun fact for the day. All right, so we're talking about GCMs, and this is just another graphic that I found to kind of help illustrate how these GCMs work. This is straight from the IPCC report, the AR4 one that we were talking about a little bit ago. It was produced, well, gosh, a while ago now, 15, 16 years ago. But it's a nice graphic kind of showing, again, remember that these global circulation models, global climate models, global circulation models, are built in 3 and 4 dimensions, really. 2 dimensions meaning just, north and east, right? That sort of simple direction. The 3rd dimension is the fact that you can kind of go up, and then the 4th dimension is through time. So you have values in this 3-dimensional little cube. You can think of it as like a Jello cube, right? That goes over time. So you have a different value for every minute, basically. And you have all these fluxes and all kinds of things that we're kind of counting for in this conceptual model, right, of how the climate works. It's embedded within each of these little cubes. All right, so we've got these global circulation models. And I mentioned in class the other day and in the previous lecture, there's about 24 global circulation models that were used for the IPCC 4 report, that AR4. It got bumped up to 30 for the IPCC 5, and now the CMIP 6, the Comparative Model Interpretation Project is the CMIP, if you see that out there. The CMIP 6 now is coming out, and there's 36 models now. So we have all these models, right? And what these do is allow us to test on all these different assumptions about how the climate is working now and in the future. And so the chapter kind of ended with this attribution study kind of thing, where basically, we've been able to use these global circulation models now that they're built to look back at time, back all the way to the paleoclimate, right, using the proxies that we have to sort of, test the model, see how it behaves. But we have this ability to sort of test out these forcings now. So remember, we were talking about forcings a couple of weeks ago, and how we parameterize there. How do we estimate how much heat flux is moving from one thing to the next, or how do we like parameters or estimate really the impact of carbon, right? We know that we've measured it, and we know that theoretically it's a greenhouse gas, but we can't actually prove it, except for the use of these models, these climate models. And so that's what this is showing, is that with just the natural forcing, so all the things that we understand naturally that occur naturally to drive climatological patterns that we see. So this is temperature anomaly again, right? So we see how much temperature fluctuates under these natural forcings. So everything from volcanoes to sunspots to solar radiation, all those kinds of things, right? And we see the CMIP3 is what we used in the AR4 report, the IPCC report that got the Nobel Peace Prize. CMIP5 is the most recent version. Again, it's just comparative model. I can't remember the exact acronym, but it's the model comparison. So basically taking it across all the GCMs. So you have the two different efforts, the older version, the newer version, and then in the black line you have observations. And the gray represents the individual model runs. So remember, these are made up of like 24 to 30 different global circulation models. So there's noise, right? Each global circulation model has a different set of parameters, assumptions. So there is noise around this, but when you average it, that's what this red and blue lines represent. So when you take the average of all those models, you can see how it follows the observations pretty well. It doesn't capture everything. We understand that, especially in the shorter time periods like these guys. But it tracks it pretty well. And it certainly tracks the trend until about here, in which case the natural forcings, all the pieces that we know impact the impact climate, it just keeps going, right? Like those are the natural systems. And it's not until you put in those human forces, both fossil fuel burning and land use conversion, that you start to explain this departure in the observations. So we can't model the observations unless we include human forcing. And that's only possible because of these global circulation models. We can't prove this in other ways because we can't go up and say, control some part of the atmosphere, inject it with a whole bunch of carbon and test the effects of warming. It's kind of logistically and politically impossible to do, right? So it's only through these global circulation models that we test against observations over and over and over again, and that we really have to take the model means from, which is what this book spent a lot of time on, that we come up with this ability to explain basically what we're seeing in our observational record. So that's really huge. So, okay, so let's look at then sort of this idea of a multi-model mean. So, but kind of covered these things, the FLATO from the IPCC. All the models reproduce some sort of observed zonal gradients, that makes really good sense. So not only does it, match the record, but it also matches our logic. It matches what we understand. All the things that we've been talking about in terms of theory and processes, it's embedded within these models, right? And so when we model it and we see it playing out well, according to what we understand, then we know that the model is performing well. We know that we've parameterized the model correctly. We've done it right? All the right forcings are in there. So we get a multi-model mean surface, something like this, that looks very, very much like what we would expect it to look like, based on our understanding of physics, based on our observations, based on all the science that we've been talking about. But they're not perfect, right? So so when you look at this multi-model mean surface, and this is what you often see when you're looking at even historic, but especially the future climate projections, you see a multi-model mean. So that's just basically saying that we're averaging out all those models. Going back to this, we're taking out all this noise and we're averaging all those models to just this single line. So that's what you're often seeing in these graphs. But there's some bias, right? There's some overestimations, there's some underestimations, and all that's really important to kind of understand. And this based on the assumptions built into these models. And when you average assumptions, well, sometimes you amplify those assumptions to the point where it really starts to generate some bad data. Not necessarily bad data, but data that's incorrect. And that doesn't mean that it's not useful. If anything, it teaches us what we need to learn, right? What else do we need to learn? So in this bias, you can kind of see there's a bit of a warm bias in the Southeast Atlantic and Pacific Ocean, right? that is probably because of the coarse resolution of ocean models that just don't capture that upwelling from the deep ocean, right? So it's estimating too warm, and it's probably because it's just not capturing that upwelling that's happening that we know because of tectonics. It's just something that the model needs to improve on, right? Some forces or some finer resolution oceanographic models to do that. Similar bias in California and in the Northeast Pacific, right? It's just a little bit warming up here, and it's probably just because of that lack of oceanographic kind of resolution. But it's important to note that, like, this is something that, sort of climate deniers would jump on and say, oh, look, like there's up to 4 or 5 degrees, departure or, degree of wrong, right? Basically, compared to observational data, what's going on? This is nuts. We can't trust it. I mean, yeah, there's some model error for sure. There's some bias in these estimates. They're estimates, right? But it's like, as the book kind of pointed out, you can generate a lot of confidence because those are smaller regions that are off, by that much. Most of it's off by a degree or two. And considering that it accurately captures the whole range of like 60 degrees centigrade pretty well over most of the Earth's surface, you can have some confidence that this is pretty good, even though in certain areas we can say we have less confidence there. Same thing with the book presented precipitation. Obviously, with precipitation, there's a bit more of a bias and some uncertainty. I've already mentioned that. Precipitation is really, really hard to dial in, primarily because we just can't. It's really hard to model cloud formation. That's the biggest thing, right? But yeah, less precise with precipitation, although certainly in general it matches the patterns that we see in real life, right? So we have some serious confidence, even though it's it's not perfect. And as long as you understand where those biases are, right, where it's overestimating precipitation, and this is just because that tropical convergence zone, right? We're just assuming too much lateral water movement up and then back down. So you account for that bias anytime you're kind of running climate models. And so since we overestimated on the oceanographic, we underestimated then in the terrestrial part, at least through northern South America. But generally, right, we're within we're plus or minus a millimeter or so a day, which is just not bad for a global circulation model. So this kind of gets at just this notion of certainty and uncertainty, and this is another graph to kind of help us just understand. So this is multi-model agreement. The reason we look at these multiple models and we average them out is just as the book pointed out, the wisdom of the crowd, proposed by Sir Francis Galton. He and we know this, right? There's been all kinds of tricks and things that suggest that this is a really appropriate way to approach things. No individual estimate or guess is ever going to be right, but when you average them out, you come very, very, very close. And this is true. This has been documented in all kinds of sciences. In ecology, we call it the multiple hypotheses theory, where if you develop lots and lots and lots of hypotheses and you compete them, you run them basically in a simulation with slight variations, you're going to arrive at the right one. You're going to arrive at the right mechanisms. So multiple competing hypotheses is the same kind of concept, but this is showing sort of, again, the models, the 24 and then the 30 models. This one developed 20 years ago. This one developed in the last 10, and how they compare to things like annual mean surface air temperature. That's this. So terrestrial average or temperature, average surface. So yeah, surface air temperature basically. Outgoing long wave radiation, precipitation, and then the short wave cloud radiative effect. And it's looking just how much it correlates um, to external data. So so we have this, well, so actually first it's correlated to the data that was used to drive the model. So we expect high correlations, but not perfect correlations. And if you don't, unfamiliar with correlations, correlations just describe how related is one data set to another. So in an ideal world, observations in these models would be both at one. So we'd have a perfect correlation. So what this is showing is that, air surface temperature is really well represented. So we've got that really dialed in. It's like 98% correlation coefficient. It's really good. And this green observation is independent temperature data. So temperature, climate data that was not used to set up these models. That's what this is showing. So it's kind of your independent validation, basically. This is internal validation, and these green dots are external validation. So temperature, air temperature, surface, like we've got that pretty well dialed in. Outgoing long wave radiation, still pretty well captured. I mean, in ecology, anything over a correlation coefficient of like 0.8 is pretty darn good. So like you're over 0.9, you're capturing that long wave radiation. You're doing that really well. Obviously, observed data sets are going to be, even better. But sometimes again, like observed data sets, one set of observed data set doesn't always agree with the other set, and we see this in the precipitation. So this independent data set is only 90% correlated, 92% correlated with the data set used to parameterize these global circulation models. And then now you start to see the separation. So each of these bars represents an individual model, and then the circles represent the averaged, the model mean. So you start to see just how much uncertainty is associated with, the original CMIP3, and then we've gotten a lot better, but we still have a significant range, right? We range all the way from like 0.73 to 0.9 correlation. Not bad, huh? And then the shortwave as well. So this just gets at model uncertainty, and it's really important to understand, just that the model uncertainty comes from the fact that we have multiple models and we have imperfect, equations describe all these processes. It's not to mean that it's bad. It's not to mean that it's wrong. It's just we're imperfect at predicting everywhere all the time. And so that's what these kind of show. I won't spend a ton of time. We'll talk about these a little bit more in class because these are a little more complicated. But I do kind of want to highlight, just these differences in like the individual models, changes in ocean heat content, right? Or the thin lines, and the multi-model mean is the red thick line compared to the actual observations, which is the black line. So you get, really decent, it all converged. I don't know why they all converged in 1971. A little bit of spread in the past, and as you move forward, it kind of spreads out, right? And this is just different, assumptions about how heat content is changing in the ocean. So this gets at the uncertainty piece, and how do you choose, right? Like what model is the best model for whatever you want to be doing? And so this, I just looked at the 5th Oregon climate assessment that we were talking about a couple weeks ago, and I've posted to Moodle so you can check this out. These are the models that they're using for Oregon. So these are the models that best perform here in our state. So they've looked at how the models capture the historic temperature changes and precipitation changes and everything, and they've said these perform the best. This is for the CMIP5, and then the CMIP6, which is supposed to come out, the next IPCC report is supposed to come out this April. So they've used the most recent version of data. So this is what they've decided is good for Oregon. And so then you can kind of focus in on just the Oregon ones, and you can kind of say, yeah, there's still some range, certainly across those 8 different models. But this best represents Oregon. And you can kind of see this is their climate sensitivity here. So basically, like climate sensitivity is just what happens when you double the amount of atmospheric carbon. And this is a little teaser for next week. The CMIP6 is actually predicting even higher than the previous one. So we might actually see some real crazy. But But look, the range of variation is increasing as well. And this is because we're getting better at understanding those assumptions around clouds and everything that really, have some significant impacts. So, so just a quick slide on like model selection. These are the four kind of criteria the European Union suggests for model selection, because, most countries are developing downscaled climate adaptation plans, and so they're all faced with this question of like, well, how do you pick the best models to represent your region? And they have these things, the vintage, right? So choose the most recent, the better. Generally, that's not always the case, but it's generally the case, right? Look at the resolution, right? The older models tend to be 1,000 kilometers with maybe 10 vertical atmospheric levels, versus the newer ones of 250 kilometers with 20 vertical levels, right? So, but thinking about that resolution, how that plays out, the validity, how does it perform according to the observations? So again, using your own data for your state or country, going in and checking it out, and then the representativeness. And this is really key, and I'm going to talk about this a lot next week. Choosing the models that perform well, but also have different assumptions about, say, the effect of precipitation and clouds and that sort of thing. Here's a website you can go check out. This is from Alaska, where they did this for Alaska, right? They chose the 5 best performing global circulation models for the Arctic and Alaska. And there's some information here. You can go check it all out. But this is the 5 that they decided. And so they use this, that's the 5 models that they said, yep, performs best for our temperature records up here, precipitation and everything else up here. And so we're going to use this 5 model average based on those 5 models. And it's going to vary depending on where you are, right? And so just to hit this home one more time, this I just downloaded from the one of the NOAA resources, that basically it's the climate models, but in the past. So this is from the year 2000 to 2020. This is monthly temperature data. And you can just see, how much variability there are in the individual models. And this is why we take the model mean. But there's an awful lot to be learned about these individual models and how they might play out in terms of future forecasts. And so that's really what we're going to hit on a lot next week, is talking about these different models and the assumptions put into them, how they play out in terms of estimating impacts and playing through the various scenarios. So we'll talk to you then.